In the summer of 2011, the largest dam system in the United States came within a razor's edge of the top of its entire flood control capacity and held back the worst flood in the Missouri River's recorded history by a margin you could measure. When the reservoir system crested, it held 72.8 million acre-feet of water. The absolute top of its exclusive flood control space was 73. 1 million acre-feet. The whole system, 6 enormous dams strung across 2,000 miles of river, filled to within 3/10 of a million acre-feet of the edge, and to keep from being overtopped, engineers opened emergency tunnels built in the 1950s that had almost never been used at 3 separate dams at the same time. And 100 miles downstream, a nuclear power plant sat surrounded by floodwater. This is the story of the 2011 Missouri River flood, the summer that record water pushed a system of dams built more than half a century ago right up to the limit of what it was designed to survive. Every number in it comes from the Army Corps of Engineers and federal records. The dams did not collapse. That is the crucial fact, and we will come back to it. But how close they came and what it cost to keep them standing is a story that anyone who lives downstream of aging infrastructure should understand, because 2011 was not a freak the system was built to shrug off. It was very nearly too much. Start with the system, because most people have no idea how big it is. The Upper Missouri River is controlled by 6 great dams, built by the Army Corps of Engineers under a mid-20th century program called Sloan, authorized by the Flood Control Act of 1944 and constructed across the 1940s, 50s, and 60s. From upstream to down, they are Fort Peck in Montana, Garrison in North Dakota, and then Oahe, Big Bend, Fort Randall, and Gavins Point across South Dakota and into Nebraska. Together, they form the largest reservoir system in the United States. They hold back the snowmelt and rainfall of the entire upper basin, generate the majority of the region's federal hydropower, and protect more than 2 million acres of downstream land from flooding. These are not slender concrete arches. Most of them are colossal earthen embankments, engineered mountains of rolled earth, some of the largest such structures ever built. That flood protection came at a heavy and often unacknowledged cost, and it is worth naming. The reservoirs that filled behind these dams drowned some of the most fertile bottomland in the northern plains, and much of that land belonged to Native American nations. The Garrison Dam's reservoir flooded roughly 150,000 acres of the Fort Berthold Reservation, home to the 3 affiliated tribes, forcing the relocation of the great majority of their people from the river valley they had lived in for generations. The reservoirs behind Oahe, Big Bend, and Fort Randall inundated large portions of the Standing Rock, Cheyenne River, Lower Brule, and Crow Creek reservations. When the contract selling the Fort Berthold land was signed in 1948, the tribal chairman wept openly at the ceremony. The dams that would go on to save Omaha and Kansas City from flooding were built, in part, by flooding out communities that had far less say in the matter. That history is inseparable from the infrastructure itself. The last dam in the chain, Gavins Point, is the one that matters most for everyone downstream. It is comparatively small, with far less storage than the giants above it, but it is the final control point, the tap that decides how much water flows down towards Sioux City, Omaha, Kansas City, and eventually St. Louis. Whatever Gavins Point releases is what the lower river must carry. And in the summer of 2011, Gavins Point was releasing water at a rate no one had ever seen. To understand why, you have to understand that 2 separate disasters arrived at the same time, and the system was never designed for both at once. The first was snow. Through the winter of 2010 and into 2011, an enormous snowpack had built up in the Rocky Mountains and across the northern plains. By spring, the mountain snowpack feeding the upper Missouri was measured at 212% of normal, more than double. That snow was going to melt and run into the reservoirs no matter what. It always does. The system is built to absorb a big snowmelt. What it is not built to absorb is a big snowmelt plus a second catastrophe stacked directly on top of it. That second catastrophe was rain. In the last half of May 2011, the Upper Missouri Basin received nearly an entire year's worth of rainfall in about 2 weeks. Not a year's worth for a wet spell, a year's worth, dumped onto ground that was already saturated and already shedding a record snowmelt. The two combined into something the record books had no equal for. Consider the runoff figures, because they are almost hard to believe. The runoff into the Missouri above Sioux City in May 2011 was 10.5 million acre-feet, the third highest single month ever recorded. Then June was worse, 13.8 million acre-feet, the highest single month of runoff since the Corps began keeping detailed records in 1898. Put May and June together, and you get 24. 3 million acre-feet in 2 months, just short of the entire normal runoff for a full year, which is about 24.8 million. A full year's worth of water came down in 60 days. By the time it was over, total runoff for 2011 reached 61 million acre-feet, making it, in the plain language of a congressional finding, the worst flooding in the river's recorded history. All of that water drained toward the same 6 dams. And the operators faced the oldest and cruelest dilemma in dam management, the one with no clean answer. Part of what made 2011 so dangerous was the timing of the two disasters, and it is worth understanding because it explains why the system got so full. The dams are operated on an annual plan. Every spring, the Corps forecasts the coming snowmelt and manages the reservoirs to catch it, holding some space open, letting some water through, balancing the year's expected runoff against the room available. By the time the record May rainstorms hit, the system had already been managing for a very large snowmelt. It had already committed much of its available space to the snow that was coming. And then a second flood's worth of water, a near year's rain in 2 weeks, arrived on top of a plan built around the snow. The reservoirs did not have room for both, because nothing in the operating assumptions imagined both would happen together. The operators were, in effect, trying to catch 200-year events in a bucket sized for one. From late May onward, they were no longer managing a normal season. They were reacting, week to week, to a volume of water that exceeded anything the forecasts or the design had prepared them for. Here is the trap. When water pours into a reservoir faster than you let it out, the reservoir rises. If it rises to the top of the dam and pours overtopping, an earthen dam can be destroyed, eroded from the crest down until it fails and releases everything it was holding in one catastrophic surge. So you cannot simply hold the water. If you hold too much, you lose the dam. But the only alternative is to release it, and everything downstream, every levee, every town, every road, and the river channel itself can only carry so much. Release more than the channel can handle, and you flood the valley on purpose. In 2011, with a year's runoff arriving in 2 months, the Corps was forced into the second choice. To save the dams, they had to open them up and flood hundreds of miles of the valley below, deliberately, for months. So they released water at rates never before seen in the history of the system. The peak releases from the dams in 2011 read like a list of broken records, about 65,900 cubic feet per second at Fort Peck, 150,000 at Garrison, 160,000 at Oahe, 166,000 at Big Bend, 166,000 at Fort Randall. And at Gavin's Point, the final gate before the lower river, the release peaked at 160,700 cubic feet per second on the 27th of June. To grasp what that number means, you have to compare it to what came before. The previous all-time record release from Gavin's Point was 70,000 cubic feet per second, set in 1997. In 2011, they more than doubled it. And they did not do it for a day or a week. Gavin's Point releases stayed above 100,000 cubic feet per second for 85 straight days. For nearly 3 months, the last dam on the upper Missouri poured out more than twice its previous record, continuously, because the water coming in gave them no choice. Even with those historic releases, the reservoirs kept climbing, and this is where you see how close the whole thing came. As the system filled through June, its total storage rose into the very top of its capacity. It crested at 72.8 million acre-feet, and the top of the exclusive flood control zone, the highest water the system is designed to hold before it is truly out of room, is 73. 1 million acre-feet. The entire system came to within 0.3 of a million acre-feet of the ceiling. Individual dams were pushed past their normal limits. Surcharge storage, the emergency space above the normal flood pool, had to be used at both Fort Peck and Garrison, and brand new record pool levels were set at Fort Peck, Oahe, and Fort Randall. The reservoirs were higher than they had ever been in the more than half a century the dams had existed. And to manage all of that, the operators reached for tools of last resort. Emergency spillways were operated at every one of the dams except oahe. And the emergency flood tunnels, release tunnels built into the dams back in the 1950s. Designed for exactly this kind of extremity, and almost never actually needed, were opened at 3 of the dams to move water and prevent the reservoirs from overtopping. These were the safety systems of last resort, the ones the original engineers put in and hoped would never be used, and in the summer of 2011, they were all in service at once. The strain was not just theoretical, and it left marks on the concrete. The sustained, extreme releases at Gavins Point damaged the foundation of its spillway slab. Investigations afterward found voids opening up beneath the concrete, and repair programs had to be launched to patch and reinforce a structure that the flood had quietly chewed at for 3 months. The 60-year-old infrastructure did its job, but it did not come through unscathed, and the damage underneath the spillway was a physical reminder that the system had been asked to do something near the outer edge of what it could take. Downstream, the consequence of all that released water was months of disaster. The flooding stretched from Montana to Missouri and lasted through the summer into the fall. High releases from Gavins Point contributed to levee failures along the lower river, including a reported 300-foot full breach near the point where Iowa, Missouri, and Nebraska meet, which sent the river across farmland and threatened the town of Hamburg, Iowa. Interstates 29 and 680 north of Council Bluffs were closed for months. Around Omaha, an army of volunteers and workers spent the summer sandbagging and patrolling sodden levees, holding the line by hand. When it was finally over, the 2011 flood had caused more than $1 billion in damage, wrecked homes and towns and farm fields and roads across 7 states, and claimed at least 1 life. What made it especially punishing was how long it lasted. This was not a flash flood that crested and receded in a day. Because the releases had to stay high for the entire summer to keep evacuating water from the overfull reservoirs, the lower river stayed above flood stage for months. Farmland along the Missouri sat underwater through an entire growing season, ruining crops across hundreds of thousands of acres and leaving fields buried in sand where the current had run over them. Homes and businesses in the floodplain stood in water for weeks, and the levees that were supposed to protect all of it were under relentless, sustained pressure the whole time, soaking, weakening, and in places giving way. The work to repair and rebuild the battered levee system began almost the moment the river finally dropped below flood stage in the fall, and it stretched on for years afterward. A flash flood tests a community for hours. The 2011 Missouri flood tested it, without let-up, for an entire summer. And then there was the nuclear plant. The Fort Calhoun nuclear station sits on the bank of the Missouri River just north of Omaha. As the flood rose, the river around it climbed to 36 feet above normal, surpassing the previous record set in 1993. The plant had, as it happened, been shut down since April for a routine refueling, so its reactor was not running at power. But a nuclear facility surrounded by rising floodwater is a serious situation regardless, because its safety and cooling systems still need protection and reliable power. The operators ringed the main plant buildings, the electrical switchyard, and the administration areas with earthen berms and temporary water-filled barriers called aquadams. For weeks, those barriers held back up to 2 feet of water from critical areas. Then, on the 26th of June, one of the aquadams was punctured. Water rushed in and surrounded some of the plant buildings and the main electrical transformers. The plant managers disconnected from the off-site power grid and switched the station's safety systems over to on-site emergency diesel generators, running the plant's protection on backup power until it was confirmed safe to reconnect. It was contained. There was no release, no meltdown, and the situation was brought back under control. But for a stretch of that summer, a nuclear plant on the Missouri was islanded in floodwater and running its safety systems on diesel. And the margin for error at a place like that is not one anyone wants to test. It was one more piece of critical infrastructure that the 2011 flood pushed to the edge of its defenses. So step back and take in what the summer of 2011 actually demonstrated, because it is the real point of this story. The largest dam system in the United States, built more than 60 years ago, was hit by the worst flood in the river's recorded history, a once-in-a-lifetime collision of record snowpack and a year's rain in 2 months. And it held. The dams did not fail. Nobody downstream died in a dam collapse, because the operators made the hard, painful choice to release record volumes and flood the valley deliberately, rather than risk losing a dam. That is a genuine success, and it is worth honoring the engineering and the decisions that made it possible. But look at the margins. 0.3 of a million acre-feet from the top of the system's capacity. Record pool levels at 3 dams. Surcharge storage tapped. Emergency spillways at 5 of 6 dams. 1950s emergency tunnels opened at 3 of them. Spillway concrete damaged from the strain. 85 days of releases at more than double the previous record. $1 billion in damage, and a nuclear plant on backup power. That is not a system that handled the flood comfortably. That is a system that survived it by the narrowest of workable margins, using every emergency tool it had, and took real damage doing so. The Corps' own post-flood analysis concluded that even if the system had been given substantially more flood control storage, 2011 would still have been a historic flood with catastrophic downstream damage. The event was, in a real sense, larger than the system was built for. It just happened to be survivable. That is the same story playing out at aging dams all across the country. It is the same underlying condition that brought the tallest dam in America, at Oroville, within hours of an uncontrolled release in 2017, that keeps engineers permanently reinforcing Louisville Lake Dam above Dallas, and that forced the complete rebuild of Arizona's Roosevelt Dam when it was found unable to pass its worst-case flood. Infrastructure built in the middle of the 20th century to the standards and the climate assumptions of that era is now being asked to hold against extremes those original designers never planned for. Most of it holds. The question that 2011 poses, in numbers you can read off a Corps report, is how much margin is actually left when the water comes. And the answer, that summer, was 0.3 of a million acre-feet. The scale of the underlying problem is national. The United States has tens of thousands of dams, the majority of them more than half a century old, and the American Society of Civil Engineers, which grades the country's infrastructure, has for years given the nation's dams a grade of D. The number classified as high hazard, meaning failure would likely cause loss of life, has climbed into the thousands as towns and suburbs spread into the valleys below them, and a significant share of those are rated in poor condition. Estimates for what it would cost to bring the nation's dams up to modern safety standards run into the tens of billions of dollars. The Missouri mainstem system is far better maintained and funded than most. It is federal, actively managed, and constantly monitored. If a system that well-resourced could be pushed within 0.3 of a million acre-feet of its ceiling and have its spillway concrete damaged in the process, the condition of the thousands of smaller, older, less watched dams around the country is a genuinely sobering question. Now, let me be as clear and honest as this deserves about the present, because a river is not one story. As of this summer, in 2026, the Missouri River main stem system is not being overwhelmed by floodwater at all. It is the opposite. The basin is in a lower than normal runoff year, with the Corps managing reduced releases. There is no main stem dam collapsing on the Missouri right now. The catastrophic flooding that has been in the news in Missouri this July is a different event on a different river, a 1-in-1,000-year flash flood on the Black River in the southeastern part of the state, which swept through campgrounds and towns and prompted hundreds of rescues. It is a tributary rainfall disaster, terrible in its own right, but it is not the main stem dam system failing. The 6 great dams are doing their quiet work in a dry year, and that whiplash, a system pushed to the brink by too much water in 2011, managing too little water in 2026, while a tributary drowns campgrounds in 1,000-year rain the same summer, is itself the deeper pattern. The Missouri has always swung between drought and flood. What is changing is the sharpness of the swings, longer dries and wetter, more sudden wets, delivered by exactly the kind of extreme rainfall that fell on the Upper Basin in 2011 and on the Black River in 2026. The dams were designed for a more moderate river than the one the climate is increasingly producing. As of this afternoon, the 25th of July, 2026, the 6 dams of the Upper Missouri stand as they have for 6 and 7 decades, their reservoirs low, their spillways quiet, the emergency tunnels shut. There is no wall of water bearing down on them today. But the summer of 2011 is the number that should stay with anyone who lives below them. The largest dam system in America, built more than 60 years ago, held back the worst flood in the river's history, and it did it by 0.3 of a million acre-feet with every emergency system it had running at once, by choosing to flood the valley in order to save the dams. The dams held. They were built to. But 2011 was the summer the river reminded everyone how much water it can actually bring and how thin the margin becomes when it does. The infrastructure is 60 years old. The floods are not getting smaller, and 0.3 of a million acre-feet spread across a system that size is a very small distance from the edge.